Today we will see how to find kth smallest element in a binary search tree. And this k can be any fixed number also. It can be given like third smallest element, fourth smallest element, or it can be given a general kth smallest element. And here it's not a binary tree, it's a binary search tree. And we know that in binary search tree, for any node, if you look at root, you can look at any other node. All the elements in the left subtree are smaller than this root node, and all elements in the right subtree are larger than it. So here 6 is larger than 5, and in the left subtree we have 3, 2, and 4. So all of them are smaller than 5. Similarly, if you look at 3, you will see that in the left side it's 2. If there are more elements, these will be smaller than 3. So if it has a left child, it will be 1 or it can be smaller. So here also its property is valid. On the right side, it's 4. So this is larger than 3. So how can we find kth smallest element? So we know that if we do in-order traversal of a binary search tree, then the result that is printed is sorted. So what in-order traversal does? Let's see it on an example first. So first we will understand in-order traversal. If we know in-order traversal, then this problem should be very trivial. So in-order traversal for a root means that first do in-order traversal of root dot left. This left denotes the root of left subtree. So all the nodes in the left subtree will be visited first. So visit everything here. Then visit 5, then visit everything here. There can be a big tree here also. So then after doing this, after this call completes, this will again call for its left and right. So once this call terminates, it would have printed all 3, 2, and 4. Then we print root. And then we do in order of root right. This is the in-order traversal. So after this returns, it would be printing 2, 3, and 4 in some order. Then we will print 5. Then we will print the right subtree, which is 6. So it will call for 3. So what 3 will do? Before printing 3, do the in-order traversal of left. So it will come here. Here left and right are null. So left will return empty. Right, then it has to print itself, so it will print 2. Then it will do it for right subtree, which is null, so it will not print anything. Then it will return to the calling function. So 3 had called this. So the call has returned from the left subtree of 3. So it will print 3 now itself, the root. Then it will call it for right subtree, which is 4. So 4 will do it for left and right, which are null. So for left it will be null return, then print itself 4. For right it's null, and then return back here. So this, all the 3 things have completed at 3. So this 3 will again return to 5. That I have done my job. Now you can print yourself. So then 5 is printed. Then it calls in order for its right subtree, which is rooted at 6. So what 6 will do? It will call for left subtree, but it's null. So this is done. Then it will print itself, which is 6. Then it will do in order on its right, which is also null, so it returns. And finally, everything returns back to the top stack. And this is the result. So you can see this is sorted due to this binary search property. And if we are asked to find third element, it will be third from the left in this in-order traversal. So one way would be that you do in-order traversal, complete in-order traversal, and then store it in an array and then print the kth element. But we can do some optimization here. Once we have visited 3 nodes, that is once this print is called for 3 nodes, we stop there and return that element. We keep track of a count. So every time we print, this print denotes that we are done with this element. I mean, we have visited this element, this node. So whenever we are printing, instead of printing, here we will not be printing it, but we will be just incrementing the count instead of print. So when 2 was about to print, we were here. So we make count equal to 1. When it returns, we print 3. So instead of printing 3, we make count equal to 2. Then it calls for its right subtree, and here left is null. So we want to print 4, but instead of printing, we make count equal to 3. So every time we are printing it, instead of printing, just increment the count and add a check that if count equal to 3, or in general, in our case, it will be k, then return this value. This will be the result. Result will be this root.value, which we were printing here, and we don't need to proceed further. So this will terminate when the count becomes k. So if there is a in-order traversal of a tree, and it's a big tree, and let's say k lies here, then once we have printed it, we will stop. So we will only visit these many nodes. So the time complexity will be order n. So let's write the code for this. First we will write in order traversal, then we will modify it the same way. Not much modification is needed. So let's write it in C++ first. So they are also telling about this in order traversal. But we will not take this route, that is modifying the BST node structure. We don't need that. So let's write it. So we need to keep track of count and result. So we will create another function. And we need to pass count and result by reference, since we will be doing recursive calls, and all of those recursive calls should have access to the global value of count and result. So we will be passing it by reference. So if left is there, do this for left, k, count, and result. And then here we would be print root.val. This would be the original in order traversal. So instead of that, we will just keep track of how many elements we have printed. We are not actually printing, but just keeping track of the count. And if count is equal to k, then we can stop here. Result equal to count, and also return from here. And do the same for right. So let's try. So it works for this case. Let's try the second one, which is a bigger example. K is 3. and it matches the expected answer. So let's go ahead and submit. And we got a wrong answer. Okay, so this looks a bit funny. If count is k, then result should not be count. It should be root.val, the value which we were printing. I should have copied this one. Let's try to submit. And the solution is accepted in C++. Sorry for that mistake. That was a silly mistake. Now let's do the same thing in Java. So here we will use atomic integer since we need to pass it by reference. To get the integer value stored in atomic integer, we use get, and its return type is int. So we are returning int. And result is atomic integer. So we will set it result dot set. So let's see. The count is atomic integer, not just integer. So we can do count dot set equal to, in count dot set we can write count dot get plus 1, but we have a ready-made function in atomic integer for that. So it's get and increment. Another is increment and get. So looks like similar to plus plus something, or like plus plus count or count plus plus. So we will use this ready-made function here, and let's try again. And this works as expected. So let's submit. And the solution is accepted in Java as well. Finally, we will do it in Python 3. It's nothing but just in order traversal with slight modification. And here we will put it in self. We don't need count and result since they are present in the self itself, so we can get it from there. Let's submit. And the solution is accepted in Python as well.